Welcome, it's Paul with a short script designed to show you how you can convert data into an abstract vector space with an inner product. I'm going to do in some detail a two-dimensional example, trying to stick very closely to the presentation in the Hubbard textbook, and then show you a larger dimensional example without much theory behind it. Hopefully this will give you some ideas for a term project. So, for my two-dimensional example, I'm going to load up that set of SAT scores. Recall we've got math and verbal scores from an unnamed high school. I'm growingly more and more suspicious that these data are completely phony, but they'll work for illustrative purposes. Following the Hubbards, the first thing I'm going to do is to subtract off the mean from these scores to produce centered random variables. And recall that if you give R a vector that's too short, it just extends it until it's the right length. So this will subtract off the mean from the math scores. The next one will subtract off the mean of the verbal scores from the verbal scores. And we can look at what we've got in a scatter plot with the centered math scores horizontal, the centered vertical, the centered verbal scores plotted vertically. And I think you can see there's a general trend toward having high math scores go along with high verbal scores. Now, following exactly the approach of the Hubbards, I'm going to scale each component of one of these data vectors by the square root of its probability. In this case, I'm assuming that each row in the data frame is equally likely, so the probability of one point in the sample space is just 1 over the number of rows. So I take 1 over the length of one of these centered vectors, and I make a new data vector. The Hubbards represent it by a capital phi, so I'm going to call it math.phi, and I'm going to get that by multiplying each component by the square root of the probability, both for math scores and verbal scores. The advantage of doing this is that then, although we had from the start an abstract inner product that satisfies the axioms, this abstract inner product has now turned into the ordinary dot product. So, in particular, I can compute the length of a vector by taking the sum of the squares of its components and taking the square root of the result. So there's the length of the math vector. There's a much easier way to get that. I just ask for the standard deviation of the math scores. And the two things are not quite the same because here I divided by n, the number of entries. R divides by n minus 1, trying to estimate the standard deviation of the population. But we've got so many samples, the difference is insignificant. I do the same thing with the verbal scores. And now for real fun, I can compute the inner product of these two vectors. That's just the dot product. I multiply them together, component by component, to get m dot v. Of course, R is happy to do that if I just ask it to compute the covariance of these two random variables. Again, the two numbers are not exactly the same because we divided by n and R divided by n minus 1. So now I've got two vectors. I know their dot product, I know the length of each, and of course I can compute the angle between them. So the cosine of the angle between the centered math scores and the centered verbal scores is 0.35. If these were uncorrelated, the corresponding vectors would be orthogonal to one another and the cosine would be 0. Of course, there's a much easier way to get this number. I just ask R, what's the correlation between the math scores and the verbal scores? And in this case, I get exactly the same answer because in both the dot products and the lengths r divided by r minus 1, the effect of doing that totally cancels out. If I want to go really geometric, I ask, what's the arc cosine of this value of the cosine function? And I multiply by 180 over pi to convert radians to degrees and say, these two vectors make a roughly 70-degree angle with one another. Of course, I can do everything in one line. In R, I bind together the column of math scores and the column of verbal scores to make a matrix, and then I pass that matrix to the variance function, and I get the covariance matrix. Variances down the diagonal, covariance on the off diagonal. It's a 2 by 2 symmetric matrix, and it therefore has two real eigenvalues. Next week, I'm going to prove that this is true in general by proving the so-called spectral theorem, and also give you a nice new algorithm for finding the eigenvalues in this case. But I'm assuming you all still remember how to compute eigenvectors and eigenvalues. If you don't, go back to week 4 of Math 23A. So I'm going to reconstruct and name this covariance matrix, and then call the R function eigen. What does that do? It gives me the two eigenvalues, and it gives me the corresponding eigenvectors. And this is a change of basis matrix, isn't it? My old basis consisted of math scores and verbal scores, and that was a rather silly basis to use because I was using in a two-dimensional space two vectors with an angle of 70 degrees between them. Now I'm going to switch to a new basis, a basis of eigenvectors, which are going to be orthogonal. So let me get the vectors back and give the resulting matrix a name, and there's only one choice for the name. This is a change of basis matrix, so we call it P, and each column of the matrix expresses a new eigenvector, a new basis vector, an eigenvector, in terms of the original basis vectors, math score and verbal score. So, if I want to compute the new eigenvector in terms of the old one, what I have to do is take math times this entry plus verbal times that entry. I see these both have minus signs on them. I think it would probably make more sense to change those minus signs to plus signs, so I will multiply both eigenvectors by minus 1. So now I've got two new random variables, nu1 and nu2. They're both linear combinations of these modified math and verbal scores. And my change of basis matrix, you may have noticed, is accomplished by a matrix where not only are the columns orthogonal, each of them has a length of 1. So this is a rotation in our two-dimensional space. Each of my new random variables is an eigenvalue, and I can check that by taking the sum of the squares in nu1 and the sum of the squares in nu2 and reminding myself what were the eigenvalues I got. The results are not exactly the same. This is again a problem with dividing by n minus 1. Not a big deal. And furthermore, these new random variables are orthogonal vectors. If I take their dot product, thinking of this in terms of a vector space, I get 0. If instead I take the expected value of their product, I get 0. That shows they're uncorrelated vectors. And if I do a plot of nu1 and nu2, you can sort of see they're not correlated with one another. There's roughly the same number of points in each of the 4 quadrants. Now, if I want, I can go back and add these new random variables to my data frame. I chose to multiply each eigenvector by -1. So here are 2 new columns, SAT nu1 and SAT nu2. And now when I look at my data frame, I've got these 2 extra columns. Now comes the real challenge when you do this. Can you interpret these new eigenvectors? Well, I look at nu1 and I see it has large values when both the scores are high. It has small values when both the scores are low. And it's actually very close to a multiple of the sum of the math and verbal score. So I might say, I've found something that measures overall academic skill to the extent that I believe that the SATs measure academic skill at all. What about the second one? Well, when I look at the second one, I see I get large values when the verbal score is significantly larger than the math score. I get negative values when the math score is higher than the verbal score. And I found a new way of looking at SAT scores. I say the most important thing, most important because it accounts for about 2/3 of the variance, is something that is very close to the sum of the 2 scores. And then I supplement that with something that accounts for about 1/3 of the variance, which is basically related to the difference in mathematical and verbal skills. These 2 random variables are uncorrelated, so if I give you these 2 things, I've specified in perhaps a more interesting way the content of the SAT scores. And because I used eigenvectors of length 1, the sum of the variances is unchanged. If I take the sum of the variances of my old math and verbal scores, I get 12,500. If I use my new variables instead, I get exactly the same number. So this is the simplest case of so-called principal components analysis. You'll be seeing a lot more of this next week. But just as a tease, I'm going to do this in a 6-dimensional space. We have a data file with some batting statistics from Major League Baseball in 2016. It's got all sorts of data about all sorts of players. And what I'm going to do is to extract from this 6 statistics, and for each of them I'm going to scale by the number of plate appearances. So my first one is going to be runs scored per plate appearance. The next one is going to be the number of singles, hits minus doubles minus triples minus home runs per plate appearance. Then the total number of doubles and triples. Since the number of triples hit in baseball is very small, I chose to lump that together with the doubles. Then home runs per plate appearance, runs batted in per plate appearance, and walks per plate appearance. It's because I'm including walks that I divided by plate appearances rather than at bats. And now I'm going to bind these 6 new variables together as columns to get a matrix that has 6 columns and lots of rows. And from that, I'm going to form the covariance matrix. But what I'm really doing is multiplying the transpose of this matrix A by A itself. So we're using the same A transpose times A operation that we were using in computing volumes of manifolds by parameterization. So here is the covariance matrix. It's a 6 by 6 matrix, and I guess I really should show it to you. Whoops. Oh, never edit while recording a script, but okay, we got it right this time. And if you look at this, you'll see that most of these statistics have a positive correlation, but some of them don't. For example, the number of singles is negatively correlated with the number of home runs. The number of walks is slightly negatively correlated with the number of doubles and triples, and so on. Here are the eigenvalues and eigenvectors of this matrix. And when I look at this, I see that the first eigenvector accounts for about twice as much variance as either the second or third, which in turn accounts for several times more than any of the others. And it may be that with three so-called principal components, three orthogonal vectors in this six-dimensional space, I can account for much of what I want to know about a hitter in baseball. Well, the vectors form a change of basis matrix. Let's give it the right name, P. Here's our change of basis matrix. It is a matrix of eigenvectors. Each column of this matrix tells me how to express one of my new random variables, a new eigenvector, in terms of my original old basis vectors. But now those aren't standard basis vector 1, 2, and so on. They are the number of runs scored per plate appearance, the number of singles per plate appearance, and so on. So I do genuinely have two different sets of basis vectors in my six-dimensional space. The eigenvectors have the nice feature that they lead to uncorrelated random variables. Since this game is called principal components analysis, I will use PC for the new set of variables, and by drawing a nice diagram, getting the matrices of the right shape in the right place, I ascertained that I can do this by matrix multiplying A, that's a matrix that has 6 columns and lots of rows, by my 6 by 6 matrix P, and here's what the resulting matrix looks like. What does this tell me? It tells me for each of my players the value of the first new random variable, the second, and the third. And on looking at these and thinking about baseball, I looked at the first one and said, this has a very high amount of runs batted in included, if I ignore the minus sign. It has a substantial amount of home runs built into it, if I ignore the minus sign. It has a substantial amount of walks built into it, and that's fairly reasonable because pitchers like to pitch around folks that hit home runs, so I decided to call this one slugger. The only distinctive feature I could find for the second one was that it has a remarkably large coefficient on the number of walks, so I called it walker. And then on the last one, it has a high coefficient for the number of runs, not so much for the number of RBIs. Maybe these are people that tend to score a lot of runs. And of course, these are orthogonal vectors in a six-dimensional space. They correspond to uncorrelated random variables. And conveniently, these three principal components account for most of the variance. If I add up the variances of my three new random variables, I get 0.0030. If I used all 6, remember the sum of the variances is the same before and after the transformation, I get 0.0035. So with half the number of variables, I'm accounting for 6/7 of the variance. And now I can add these on as extra columns in my data frame: slugger, walker, and scorer. Now comes the fun. If we want to try to get a better identification of what the first principal component means, we sort our data frame. I'd never done this before, but after a little bit of snooping on the internet, I found out how to do it, and I even discovered that if I put a minus sign here, I can get sorting in descending order. And who's right at the top of the list? The quintessential slugger, David Ortiz. So these, by and large, I'm a little out of touch with Major League Baseball these days, are genuinely sluggers. If I sort on the second one, I get quite a different set of people. I do get folks that seem to draw a very large number of bases on balls and who tend to score many more runs than they bat in. That's also true in perhaps an even more extreme way for the top people if I rank according to the third of my 6 new vectors. And interesting, I never took stolen bases into account, but the folks that score high on this one actually have a substantial number of stolen bases if I compare them, for example, with my original sluggers. I never realized David Ortiz stole even a single base. The pitcher must not have been watching. So this is a standard technique in data analysis that makes good use of the linear algebra you've learned. I'm going to go into much more detail on this next week, but since I'm going to ask you to start thinking about a term project this week, I wanted you to have this possibility in mind.